Hello, this is Anthony Schmitt. I'm in Section B of Machine Design 1, and I'm here today to talk about springs. There are many different applications of springs in engineering and machine design, so let's take a look at these springs and see how we can apply them and how we can analyze how they function. All right, so let's get started. Okay. First thing we want to go over are the main functions of a spring. Now, the first one is to exert a force. Now, an example of this would be, say, maybe in a pellet gun, the spring is pulled back, and when it's released, it exerts a force on the pellet and shoots it out of the barrel. The next function is to provide flexibility. Now, a good example of that is a trampoline. It's got the main trampoline part, and it's attached to many springs around, and it makes it a flexible base to land on and bounce off of. And the third is to store / absorb energy. And an example of absorbing energy is the shocks on a vehicle. Allows it to take bumps and any thing like that, and makes it affect the movement of the car less. Another example of storing energy would be the spring in the pellet gun. You store the energy in the spring and then release it, and it exerts that force. Okay, so we know the functions of a spring. Now as engineers, we want to design one, and the things we need to consider are here. First is stress. What kind of stresses are we going to see in a spring, how they act? The deflection. For example, in a compression spring, the string is being compressed, and we want to know how far it's being compressed. We want to know the stability of a spring, whether or not it's going to compress or extend uniformly, or if it might buckle. And then the strength, if we're going to make sure the spring is strong enough. So before we get into those, I want to look at the anatomy of a spring. This is a cross section. So imagine the spring is cut in half long ways like that. And we can see here the wire diameter is small d, and that's the diameter of the actual wire that the spring is made up of. Think about the wire being coiled around. Think of it as a long wire that's coiled around to a spring, and that's the wire diameter. Next is the coil diameter, and coil diameter goes from the center of the cross section here to the center of the cross section here, and that represents the diameter of the entire coil across. Now the ratio of the coil diameter and the wire diameter is called the spring index, and that's symbolized with the capital C, and we'll use that later to calculate our stress. Now for our stress, we have the max shear for a helical spring, but to calculate that we need the shear stress correction factor, and that can be one of two. The first is for direct shear, Ks, and that's equal to 2C plus 1 over 2C. And that's if you only have direct shear. If you also have curvature, you need a different equation. And this is a constant KB, which is equal to 4C plus 2 over 4C minus 3. And this, the KB accounts for direct shear and the curvature effect. So if there's only direct shear, you use K of S. If there's direct shear and curvature, you use K of B. And that's to calculate the max shear for a helical spring, which is K times 8 F, the force, times big D, the coil diameter, over pi little d, the wire diameter, to the third power. And this will either be K of S for direct shear or K of B for direct shear and the curvature effect. Alright, now to get into deflection. Now, from physics, we know the spring rate, or the spring constant, is K equals F, the force applied to the spring, over X, the deflection of the spring. But we can't always just use that equation. Using Castigliano's method to relate force and deflection, we can derive this equation for the spring rate, K, and that comes to be approximately small d to the fourth times g over 8 large D to the third times n. And g here is modulus of rigidity, and n here is the number of coils. Okay, so moving on to stability. When we look at stability, we look at the free length, which is L naught. And what the free length is the total uncompressed, unstretched length of the spring before the forces enacted on the spring to compress it. What we know about stability is the absolute stability is achieved when L naught is less than pi d, large D, over alpha, which is the end condition constant, times the square root of 2e, which is Young's modulus, minus g, over 2g plus e. And for steel, we can calculate all that and go ahead and say this is 2.63 large D over A, the end condition constant. And this is just something that we can memorize because steel is the material we use most often for the wire of the spring. Alright, so let's talk about strength. When we have a problem with springs, or for designing springs, we need to know the type of the spring ends. And in problem statements, we usually be given which type it is. And when we're given which type it is, we can go and see these equations for each of these terms. One of the most important ones is NT, which is the total coils, which is not the same as the N in the equation for the spring rate. This N is N sub A. Well, the total coils is N sub T. And depending on the spring end, it'll be different. So common one is plane and ground or squared and ground. Say you have a total coils of 15, that's given in the problem. NA would be total coils minus 1, because the total coils N sub T is NA plus 1. So you would find NA from that to plug into there to find your spring rate. We have the free length here. We've talked about the free length. For example, for plane and ground, it's P, which is the pitch, which is the distance between each coil, times Na+1. Then you have the solid length, which is the length of the spring after it has been compressed with whatever the displacement is that is for the problem. Okay, and then to estimate the ultimate tensile strength of a spring, we'll have to use the table, which is table 10.4, which is in the textbook. You can see it here. It has a number of different values depending on what kind of material you're using. We use that here, the wire diameter D. So the equation is ultimate tensile strength is A over D to the M power. And A and M can be found here in this table. And then D is your wire diameter. Another important equation related to strength is tau equals strength over a factor of safety. We know tau from earlier, it's the max shear stress. And we have the strength over the factor of safety. Those are important, knowing safety factors. And another little thing that's important is the fractional overrun, which is symbolized by the Greek chi. And this is important because in a spring, the force at the closure, F of S, is not the same as the maximum force on the spring. And that's because mostly a spring, the force deflection curve shows a linear profile. However, once it gets more and more compressed to where all the springs start to touch, the number of active turns diminishes, and so more non-linear behavior occurs. And so what we have is force at closure is equal to 8/7 of force max. And this 8/7 is 1 plus chi. And we know chi to be 1/7. And that's basically it for all we need to know about designing a spring. At this point, you can start taking on problems with springs, figuring out what needs to be figured out, and designing them ourselves. So thank you.